Okay. So, now how many, okay, so this is for these bottom subtrees, but how many bottom subtrees can there be? So, the number of bottom subtrees is again bounded by the but last size. I mean, it is bounded by the size except for the last layer, right. I mean, you cannot have number of subtrees beyond more than the size. Okay. So, the number of bottom subtrees is at most the but last size, which is at most 2 to the power 1/10 n to the power 1 over d minus 1. Okay. So, now if I take a union bound, what I get is that the probability that there exists an HI such that HI restricted to rho is not a T DNF is at most the product of these two quantities, gamma Pt whole to the power t times 2 to the power 1/10 n to the power 1 over d minus 1. Now, if I make the substitutions, that is, if I substitute the value of p, which is as n to the power minus 1 over d minus 1, and I substitute t over here as whatever 1/10 of n to the power 1 over d minus 1, what I will get, and I just simplify this thing, I will get that this is equal to, so I am just writing the simplification because I have already done it. So, this will be gamma by 5 raised to the power 1/10 n to the power 1 over d minus 1, and by our assumption that by our choice of n, we have that this is less than 1/3. Okay. So, yeah. So, now the expected number of variables unfixed is equal to p n, because with probability p I am not fixing a variable or a variable remains unfixed. So, therefore, the probability that at least p n variables are unfixed is greater than or equal to half over here. Okay. So, now we have that by our choice of rho, okay, the probability that at least p n variables are unfixed is half, and we have that there exists HI such that this is not a T DNF is less than 1/3. So, the probability that both these events are simultaneously true, okay. So, or actually the complement of this and this is simultaneously true, that is for all HI restricted to rho is a T DNF. Okay. So, note that the probability of this is just 1 minus of 1/3, which is 2/3 over here, or greater than 2/3, okay, and at least p n variables are unfixed is greater than half minus 1/3. So, how do we get this? So, think of it as this as follows. So, one way of looking at this statement is that at least half the fraction of rows that I am choosing will give me this property, okay, at least half the fraction. And this, so if I look at the negation of this, what I get is that at least 2/3 fraction of the rows that I am choosing will give me the negation of this property, which is basically this what I have written here. So, I have 2/3 fraction from here and I have half the fraction from here. So, therefore, at least 1/6 of the fraction, that is basically if I look at the common part of both these two, at least 1/6 of the fraction of rows that I have will give me both these two properties. Okay. So, this is 1/6. This is a quantity that is greater than 0, therefore, which means that there exists some row, okay, we will call it rho star, such that with respect to rho star both this statement and this statement is true. Okay. Yeah, so I do not need this anymore. Okay. Therefore, there exists a rho star such that with respect to rho star for all Hi is a TDNF and at least Pn variables are unfixed in the random in this restriction rho star. By rho star. So, now we have a rho star that we want, and now we will just do what I said at the beginning. So, I take this particular rho star, I take the circuit C and I will convert it, I will use the switching lemma and I will flip these two layers. Okay. So, from C construct C prime by replacing each Ti with the corresponding T DNF, okay, that computes Hi rho star. Okay. So, now what do we have, what can I say about C and C prime? So, C prime is equivalent to C on the unfixed variables. Okay. So, I take my circuit C. So, firstly what I do is that I construct C prime, that is basically I take that particular rho star and I apply the switching lemma, I get a corresponding T DNF, I just replace each of those Ti's with the corresponding T DNFs. So, I get this, and on the unfixed variables, on the variables that are not fixed, both these circuits are exactly the same, right. What else can I say about C prime? What can I say about the bottom fan-in of C prime? How much will it be? So, I am changing it into a TDNF. So, what will be the bottom fan-in? Huh? It is still bounded by T, right, because from a TCNF I have just changed it to a TDNF. So, the bottom fan-in remains the same, is at most T. What can I say about the size, the butt last size, the or wait one second. So, in fact, we should do one more step before I argue about this. So, next what we do is this is C actually. Next what we do is that we merge the two layers. Okay. So, now I have a TDNF over here. So, therefore, there exist, it is a DNF. So, there exist adjacent layers of OR gates. Okay. So, we just merge them to decrease the depth of C prime by 1. Okay. And let us call this circuit as C double prime. Okay. So, call this circuit C double prime. So, what we are essentially doing is that, so think of it this way. So, I have two layers of OR gates now. Okay. Now, what I do is that I just take the top layer OR gate and I just whatever was coming into the bottom layer OR gate, I just put it, I just send it to the top layer. Okay. And it is computing the same function, and we will call this circuit as C prime. By the construction, C prime has depth 1 less, and now we will argue about the bottom fan-in and the size of C double prime. So, bottom fan-in of C double prime is still bounded by T. I am not changing anything at the bottom. The butt last size of C double prime is still bounded by the butt last size of C, because I am not introducing any gates. In fact, I am reducing some gates. So, it does not change the butt last size. Okay. And yeah, so yes. Yes, because at the last layer it is an AND, because it is a DNF at the last layer. So, we are looking at the last 3 layers now. At the very last layer I have AND of literals, because it is a DNF. The one before that I have an OR of all these ANDs, and the one above it I have another OR by our initial assumption. Now, this third last and second last is what I am merging, those two ORs. The last remains the same because it is AND, because we are looking at DNF over here. So, nothing changes at the bottom, and the size of course is bounded by the initial size. Okay. So, C double prime computes parity of n on this restricted set. So, this notation means that if I look at the unfixed variables by rho star, okay. So, the unfixed variables, so C double prime is computing parity on those unfixed variables now, okay. But any restriction of parity is just parity on the unfixed variables. Okay. So, this is where I am using the property of parity. Okay. So, whatever variables that are remaining unfixed over here, so by this restriction there are some variables remaining, the parity any restriction of parity, sorry, any restriction of parity to those unfixed variables is just parity on those unfixed variables, because now if I just flip any of those unfixed variables, my parity value will change. Okay. So, this is the thing, and how many variables remain unfixed? So, I have p n variables that remain unfixed. Okay. So, therefore, what we have is, therefore, C double prime computes parity on So, it is computing parity on the unfixed variables, right, because on the other variables are fixed to some 0 and 1. So, they have become constants now. So, only these many unfixed variables remain. So, that is what we argue, that these many unfixed variables remain after this restriction rho star. Okay. So, this is C double prime is computing parity on these many variables, correct. Now, what is the value of p, or how many variables are remaining unfixed now? So, we will substitute the value of p. So, this is equal to parity of, so p was n to the power minus 1 over d minus 1. So, it is n to the power minus 1 over d minus 1 times n, which is parity of n to the power d minus 2 by d minus 1. Okay. So, on these many variables, my circuit C double prime that I have computed, which has depth d minus 1, is still computing parity, correct. Now, we will get a contradiction. So, now let us take this value as m. So, say n to the power d minus 2 by d minus 1 is equal to m. So, what do we get? So, and of course, note that by our choice this m is greater than n. Okay, we had chosen n in such a way, so that n to the power d minus 2 by d minus 1 was greater than n, and our inductive hypothesis was that for all small n greater than capital N, there was no depth d minus 1 circuit that was computing parity having a certain size and a certain Butler size. So, that is the contradiction. Okay. So, therefore, we show that there exists a depth d minus 1 circuit for parity having but last size. So, now the size will be, how much is the size? So, size will be 2 to the power 1/10 of m to the power 1 over d minus 2 if I just substitute. So, initially, so the size was n to the power d minus 2 by d minus 1. So, if I substitute, I get this, and bottom fan-in 1/10 m to the power 1 over d minus 2. So, this is a contradiction, right. So, once again, so quickly to summarize the idea. So, essentially so the proof is by induction on D. So, we assume that it is true for some D minus 1. Okay. Now, what we take is that, so now suppose there is a circuit for D that is, I mean, so suppose the lemma is not true for D, that means that there is a circuit for arbitrarily large n for D which has size bounded by this and but last size bounded by this, or the bottom fan-in that is bounded by this. Then what we do is that I assume that the circuit is in this canonical form. Okay. I take the last two layers, I apply the switching lemma, I flip them, okay. I merge the two adjacent levels which have either AND or OR gates, whatever it is. So, in this case we are looking at DNF, so I have adjacent OR gates, I merge them, okay. And I argue, so my choice of probability, I argue that, well, even after this merging, there is a very large number of variables that are still remaining unfixed, okay. So, that depends on my choice of probability. And then we argue that, well, probability on those unfixed variables is, or the parity of those unfixed variables is still a parity function, and therefore, I get a contradiction to the fact that it was true for D minus 1. Okay. Okay. So, yeah, so actually this proof somehow gives a better intuition as to why this result is true, that is, any AC0 circuit for parity must have exponential size, okay, or any circuit of depth D for parity must have exponential size, because this is somehow saying that if I have these OR and AND gates, if I take a circuit which has OR and AND gates, okay, and I flip them, okay, then with very high probability the function remains the same in some sense. Okay, so, or in other words, if I have a function, if I have, let us say, a DNF, if I take just two layers, okay, such that it is computing some T DNF or some T CNF, and I flip them, then the value does not change so much, okay, it kind of remains quite similar, okay, or it remains similar with some high probability. But parity is something that is very different. If such a thing happens, parity actually changes drastically. So, I cannot keep on doing this same thing and expect the final circuit to compute parity. Okay. Okay, so yeah, so that is all. So, next class we will try to see the proof of the switching lemma. So, actually that is quite complicated, that is even more complicated than this. We will see, I mean, how much of it we can cover, but yeah. Okay.